The fine-tuning argument for God's existence argues to God as the best explanation for the fine-tuning of the constants and quantities of physics, such as the strong nuclear force, the weak nuclear force, gravity, electromagnetism, dark energy, and others. If these laws of physics were off by even a hair's breadth, the universe would not be capable of permitting life of any kind. I covered the fine-tuning argument for God's existence in pretty good depth in the previous two videos. You can see them on the screenshots that I took here on the screen. The fine-tuning that we looked at in those two videos had to do with things that affected the entire universe. The fine-tuning we're going to look at in this video has to do with things that affect the life-sustaining capacity of our local region. In addition to the 37 constants and quantities that need to be fine-tuned for planets, stars, galaxies, atoms, life chemistry, etc. to exist, hundreds of different aspects of our galaxy, solar system, and Earth-Moon planetary system had to come together in a just right, very specific way in order for the evolution of advanced life on this planet to be possible. Any local region that's going to have life is going to need to have these parameters. Therefore, when astronomers are looking for another planet that may have life, or a planet we might be able to move to someday when space travel becomes advanced enough, they look for these features. The reason I call this local fine-tuning is that it only affects a local region. Unlike the fundamental forces of dark energy and gravity, these parameters could be way off in some other part of the universe, and we'd be okay. Unlike the strong nuclear force, the weak nuclear force, gravity, electromagnetism, etc., these things have to be just right, or else no life could exist anywhere at any time in any region of the universe. The entire universe would be life prohibiting. However, the fine-tuning parameters I'm going to be talking about in this video only have to be just right in a localized region in order for that localized region to permit life. These parameters could be way off in other parts of the universe, other galaxies and other solar systems, and we'd be just fine. It would just be those localized parameters that wouldn't be able to sustain life. That's why it's called local fine-tuning. So fire up those neurons, because we're about to use the brains that God gave us. I'm going to be talking about these locally fine-tuned features in a specific order. First, I'll talk about the finely tuned parameters that affect our home planet. Then I'll move on to describe the finely tuned aspects of our solar system, and then I'll move on to talking about the finely tuned aspects of our galaxy and galaxy cluster. After I talk about all of the examples of fine-tuning in our universe, I'll give a syllogism for intelligent design as the best explanation for why all of these parameters came together in the just right way. After I talk about that syllogism, I will then address several objections that atheists, scientists, philosophers, and laymen have against the locally fine-tuned argument. First parameter, our just right moon and just right atmosphere. In order for life to exist, we need to have a moon of very specific properties. Our moon and its formation played a crucial role in preparing the planet for habitability. Astrophysicist Hugh Ross talks about this in his documentary, Journey Towards Creation. Let's watch.
Our moon has long mystified astronomers. It is so large relative to Earth that the Earth and Moon together are often classified as a double planet system. But studies of gravity show that no such double planet can form out of a single gas and dust cloud so close to a star as we are to the Sun. The Moon must have formed later through some unusual process. Moon exploration enabled us to confirm that lunar rocks differ chemically from Earth rocks. Through study of lunar rocks' radioactive decay, researchers discovered that the Moon is in fact nearly 100 million years younger than the Earth. In the 1990s, a theory explaining the Moon's existence gained wide acceptance in the scientific community. According to this theory, an object the size of Mars crashed into the newly forming Earth about 4.5 billion years ago. Most of the object's mass was absorbed by the Earth, but this collision also sent up a huge cloud of dust and rocky fragments all around the Earth. In time, gravity pulled those fragments together into one solid body, the Moon. The Earth, meanwhile, lost its entire atmosphere, and a new, much thinner one began to form from gases released by Earth's crustal material. Such a collision may seem a disaster, but it proved just the opposite. It set in motion certain alterations to Earth's features that eventually made this planet a uniquely suitable site for life.
The odds against a collision benefiting the eventual support of human life are staggering. The planet colliding with the Earth would need to be the right size, moving at the right velocity, striking at the right angle, made of the right materials, and occurring at the right time in the development of planet Earth. If any one of these factors were off by just a few %, the Earth would be barren today.
Unless that impact had occurred, Earth's atmosphere would be much heavier than it is, even heavier than that of our neighboring planet, Venus. Venus's thick carbon dioxide-filled atmosphere would mean instant death for all possible life. The extra mass Earth gained from the collision, along with its atmospheric revision, meant that water could exist on Earth in all three states: ice, liquid, and vapor, and in huge supply. A supply absolutely essential for an efficient, consistent water cycle.
Next parameter, our just right planetary rotation speed. The Earth initially rotated so fast that a day lasted 8 hours. And boy, we complain about there not being enough hours in the day already. But the Moon slowed it down to 24 hours. A rotation speed of 8 hours would obviously be inhospitable to life because there would be 500 mile-per-hour wind velocities. However, the Moon slowed our rotation down from the initial 8 hours to 24 hours. This rotation speed of the Earth must be exactly 24 hours. Not 25 hours, not 23 hours, 24 hours. No more, no less. If it were 23 hours, the daily wind velocities would be so severe that if people were on the ground, they'd become living kites. On the other hand, a rotational speed of 25 hours would cause the temperature in the daytime to be so hot and the temperature at night to be so cold that the only way survival would be possible would be to live in air-conditioned and heated buildings from the time you were born until the time you died, and never left the air-conditioned and heated building. Obviously, these conditions are too severe to support life. Next parameter, the Moon's just right size. A 24-hour rotation speed is crucial to advance life. However, not just any old moon will get you that just right rotation speed. You have to have a moon of the just right size. If the moon that formed were too big, then the rotation rate would have slowed down too much. But if it were not big enough, then Earth's rotation rate would not have been slowed down enough, and therefore you'd have many tornadoes and hurricanes occurring every day. So the dust and rocky fragments ejected from the Earth by Theia had to coalesce into a moon of the just right size in order to slow the rotation rate down to that very narrow window of 24 hours. Next parameter, a just right moon formation scenario. As Hugh Ross said in the previously played documentary clip, in order to get a moon of the just right size, the collision scenario between Theia and the Earth had to have a variety of different factors occur just right. Theia had to be of the just right size, it had to hit the Earth at the just right speed, it had to be made of the just right material, and it had to hit the Earth at the just right angle in order to eject the just right amount of dust and rocky fragments from the Earth's crust into the Earth's atmosphere in order to come together to form a moon of the just right size in order to slow the rotation rate down to that very narrow window of 24 hours. Let's talk about these various parameters about Theia in more detail. Theia's just right size. Now, I said that in order for the moon to be of the just right size, and therefore the rotation rate of the Earth be the just right speed, Theia had to be of the just right size. Why is this? If the planet that collided with the Earth were too big, it would have either ejected the planet Earth right out of the solar system, if it were significantly larger than what it was, or it would have adopted Earth as one of its moons, if it were the size of Jupiter, for example. Either way, this would have been bad for life. On the other hand, if Theia were too small, it would not have generated enough force upon impact, which means less debris would have been shot up into the Earth's orbital path, which would mean that a much smaller moon would form, considering we were lucky enough to get any moon to form at all. What about Theia's just right speed? Additionally, if Theia hit the Earth while traveling at a much higher velocity, it would have ejected the Earth out of the solar system. Or it would have destroyed the Earth. It would have been like taking a stick of dynamite to a bowling ball. Boom! Many pieces of Earth flying in all directions. Either of these scenarios would have rendered it impossible for life to exist in our solar system. On the other hand, if Theia were not traveling at a high enough velocity, we are again faced with the problem that not enough material would be ejected from the Earth's crust into the Earth's orbit to form a moon of sufficient size. What about Theia's just right angle? If Theia hit the Earth at an incorrect angle, it would have destroyed the Earth, like taking a stick of dynamite to a bowling ball. What about Theia's just right material constitution? If Theia was made of a different material, life wouldn't exist either. Why? You see, when Theia crashed into planet Earth, the interior and exterior were totally transformed. The collision caused the planet to become rich in uranium and thorium, which are critical ingredients for starting and sustaining Earth's tectonics and magnetic fields, which I'll talk about later in this video. Several other elements infused into Earth's interior in very precise amounts, which also had an important function in the magnetic and tectonic history of our planet. The composition of Theia also played a role in the future oceans and atmosphere of Earth. All four of these factors, the just right size, velocity, angle, and material of Theia, had to be just right in order for three other factors: the size of the moon, the thin atmosphere of the Earth, and the slow rotation period of the Earth to be just right. If any of Theia's collision properties were off by a little bit, the Earth would be barren today. Next parameter: Earth's magnetic field. Reasons to Believe's Dave Rogstad explains in a blog post on Reason.org that, quote, "The Earth's magnetic field is critically important for at least two reasons. One, it provides protection for life from high-energy particles originating from both cosmic rays and from our sun. And two, it provides a shield preventing the depletion of our atmosphere from bombardment by the stream of charged particles ejected from the sun. And that the longevity of the field is based on the Earth having enough radioactive material to maintain its internal heating. This material is believed to have been enhanced by a Mars-sized collision in Earth's early history that produced the moon." End quote. Next parameter: the depth of Earth's primordial ocean. Apart from Theia needing to be fine-tuned itself in so many different ways to get a just right moon, the Earth must also be fine-tuned for this improbable moon formation scenario to go just right. The depths of Earth's oceans 4 billion years ago could have messed everything up, even if Theia did everything right. If the Earth's early oceans were too shallow, then Theia would have ejected insufficient amounts of the Earth's ocean and atmosphere into outer space. Additionally, the mass and composition of the Moon would have been altered, i.e. the Moon would have been too big as a result of Theia ejecting too much material into space. If the primordial ocean were too deep, on the other hand, then Theia would have ejected too much of Earth's primordial ocean and atmosphere into outer space. And again, the mass of the Moon would have been altered. Next parameter, the Earth's just right mass. If the Earth were more massive, then its gravity would be significantly stronger, because the more massive a planet is, the stronger its gravity is. If that were the case, then the Earth would retain large quantities of methane and ammonia in its atmosphere. In that case, the surface of the Earth would become hundreds of degrees in temperature, too hot for any life forms to bear. Not that the increased temperatures would matter. Given the increased gravity, advanced life forms would be crushed under their own body weight. You could have microbial life, but not advanced life. On the other hand, if the Earth were too small, then its gravity would be much weaker. In that case, it would be impossible for the planet to contain large bodies of water. No water equals no life. It doesn't take a genius to know that if the planet doesn't have water, it won't have life. In fact, when astronomers are scanning the skies with their telescopes looking for a planet that might have life on it, or a planet that we might be able to move to someday when space travel gets advanced enough, one of the first things they look for is water. Because no matter what else the planet might have in its favor, if the planet is devoid of water, it will be devoid of life. So the first thing that these astronomers look for when they're looking for a planet that might have life on it, that we might be able to move to someday, the first thing they look for is water. Does it have water? That is how crucial water is for any kind of life to form at all. The next parameter, the just right thickness of Earth's crust. The thickness of the Earth's crust also has to be just right in order for life to exist. If the Earth's crust were too thick, tectonic processes could not occur. This means that no land masses could form, and therefore the Earth would be completely covered in water. While water is a requirement for life to exist, so is land. Without land masses, nutrients cannot be recycled back into the ocean floor. If Earth's crust were too thin, the level of tectonic uplift would make it impossible to build advanced civilizations at best, and it would make it impossible for creatures to survive at worst. Next parameter, the just right amount of oxygen. Gotta love that oxygen, right? Well, the amount of oxygen in Earth's atmosphere is 21%. We have 21% oxygen. It's got to be 21%. We can't have any more if living creatures are going to exist on this planet. Why? Well, if the Earth's atmosphere had 25% oxygen, then fires would erupt spontaneously. You could catch on fire while walking down the street due to the frictions between your pant legs. On the other hand, if the Earth's oxygen level were 15%, then living creatures would not have enough oxygen to breathe. Next parameter, the just right amount of lightning strikes. In the book, I Don't Have Enough Faith to Be an Atheist, in the chapter on fine-tuning, Frank Turek and Norman Geisler write, quote, "If the atmospheric discharge, lightning, rate were greater, there would be too much fire destruction. If there were less, there would be too little nitrogen fixing in the soil." End quote. Next parameter, the Goldilocks zone. Any planet that's going to have any hope of harboring life has to be a planet that is neither too far away nor too close to its home star. Our planet, surprise surprise, is neither too close nor too far away from its home star. It exists in an orbit, an orbital path that astronomers call the habitable zone, or more playfully, the Goldilocks zone. It's called the Goldilocks zone because if you've read Goldilocks and the Three Bears, you'll know that when Goldilocks tried everything in the house after she barged in, Papa Bear's porridge was too hot, Mama Bear's porridge was too cold, but Baby Bear's porridge was just right. Same goes for the chairs. Papa Bear's too hard, Mama Bear's chair too soft, Baby Bear's chair just right. And the beds. Apparently Baby Bear was the only he was the only member of the household that got anything good. He got all the good stuff. Papa Bear and Mama Bear had to deal with lesser quality furniture. You give up stuff for your kids. But anyway, if our planet were outside of the Goldilocks zone, if it were too close to the sun, then the planet would become so hot that all of its oceans would boil. So if our planet were boiling, eventually it would become dry, and it would have no water. And that's bad for life, because again, no water, no life. That's the first thing that astronomers look for when they're scanning the skies, looking for a planet that might have little green men, or at least microbial life. On the other hand, if the Earth were too far away from the sun, all of our oceans would freeze. We'd have an ice planet. Our position in the solar system makes our planet neither too hot nor too cold, but just right. The next parameter I want to look at is the sun's just right size. The mass of our sun is important for the existence of life as well. Our sun is a Type 2 G-spectral dwarf main sequence star. And yes, I have that committed to memory. Aren't you proud of me? This type of star is vital for life. If our sun were smaller, like the majority of stars in our galaxy, the habitable zone would be much farther in. As a result, Earth would no longer be in the Goldilocks or habitable zone. Now you might think that that's no big deal. Maybe life could evolve on the planet that is in the habitable zone. The problem with a smaller star and a much farther in habitable zone is that any planet in the habitable zone of such a star would have its rotation completely halted by the severe tidal interaction between the sun's gravity and Earth. This means that one side of the planet would be constantly facing towards the star, and the other side of the planet would constantly be facing away from the star. One side of the planet, it would be daytime all the time. On the other side of the planet, it would be nighttime all the time. Remember that I told you earlier in this video that in order for life to exist, we need a rotational speed no more and no less than 24 hours. Well, in this scenario, we don't have a rotational speed at all. The planet's not spinning whatsoever. Moreover, with a smaller star, you'd have much more frequent and more severe solar flares, which means that a technologically advanced civilization would be impossible, even if creatures could survive at all. And on the other hand, if we orbit a star much larger than our sun, we would be bombarded with way too much solar radiation. Planets orbiting a star larger than our sun cannot sustain life because, number one, they're too hot, and number two, they produce too much solar radiation. Not only that, but the larger that a star is, the shorter its lifespan will be. Bigger stars live a lot. They don't live nearly as long as smaller stars. Smaller stars live a lot longer than bigger stars. So if our sun were much larger than it is, it would probably die out before intelligent life could even have a chance to evolve. Next parameter, the parent star's magnetic field. For a planet to have life, the star that it rotates has to have a magnetic field of the just right strength. If the sun's magnetic field were too weak, solar wind and solar magnetosphere will not be adequate to thwart a significant amount of cosmic rays. Too strong, and you end up with too great of an X-ray flux. Next parameter, the rotation rate of the sun. The previously mentioned parameter depends on the rotation speed of the life-hosting planet star. If the life-hosting planet star, for example Earth's sun, rotated too slowly, the magnetic field of the sun would be too weak. As a result, Earth would not receive enough protection from cosmic rays. If the sun rotated too quickly, there would be too much chromospheric emission, which would cause the Earth to be bombarded by too much solar radiation. Next, few parameters. The just right gas giant neighbors. In order for a planet to harbor life, it must be surrounded by 4 massive planets of the just right size and the just right distance. We have those. They're called Jupiter, Saturn, Uranus, and Neptune. These planets are important because they act as guardians that shield our planets from asteroids that try to enter our solar system from outside the solar system. For example, whenever an asteroid enters into our solar system, Jupiter, or whatever gas giant it's closest to, acts as a sort of vacuum. Jupiter's gravitational pull pulls the asteroid into itself, so Jupiter takes the hit instead of Earth. Remember that in physics, two massive bodies attract one another, and the larger those bodies are relative to one another, and the closer they are together, the more powerfully they will attract. If these gas giants either did not exist, or were of the wrong size, or were of the wrong distance from Earth, we could not survive. Extinction events like that which wiped out the dinosaurs would be commonplace. If Jupiter were too massive, its gravity would be much stronger. As a result, the Earth's orbital axis would be disrupted. We'd wobble back and forth like a weeble. If that were the case, we'd have severe temperature differences that would render the planet hostile to life. If Jupiter were less massive, then its gravity would be too weak to attract comets and asteroids and pull them into itself. Jupiter must also be of the just right distance from the planet Earth. If Jupiter were too close to the Earth, then the Earth's axis would be disrupted by its gravitational pull, causing all sorts of temperature extremes. If Jupiter were too far away, then there would be too large of a gap between Earth and Jupiter, and comets could slip by quite easily. Saturn's mass must be fine-tuned. If Saturn were more massive, then its gravitational pull would disrupt the Earth's orbital axis, causing all sorts of temperature and weather extremes. If Saturn were too small, it would be insufficient to protect us from asteroids, comets, meteors, and meteorites, because its gravitational pull would not be strong enough to grab a hold of them. Saturn's distance must be just right. If Saturn were too close, then its gravitational pull would disrupt the Earth's orbital axis, and if Saturn were too far away, there would be too big of a gap between Saturn and Earth. Phew! Asteroids would just slip by right easily. Uranus must be of the just right mass. Really? Really? You're laughing at that? Real mature. If Uranus were too massive, stop laughing. The Earth's orbital axis would be disrupted, not massive enough, and it would be insufficient to shield us from comets and asteroids. If Uranus were too close, okay, that is pretty funny. Earth's orbit would be disrupted. If Uranus were too far away, there would be too large of a gap between Uranus and Earth, and comets could slip by very easily and hurt us. For Neptune to be just right, Neptune must be of the just right mass. If Neptune were too big, the Earth's axis would be thrown out of whack. Not massive enough, and it would be an insufficient asteroid shield. And it must also be neither too close nor too far away. Too close, Earth's axis gets thrown out of whack. Too far away, and again, too big of a gap. Comets would just slip by very easily. Next parameter, Mars and Venus, the place where men and women are said to be from. Mars and Venus play a role in protecting the Earth from asteroids in the asteroid belt. In his book, The Case for a Creator, Lee Strobel interviews philosopher J.W. Richards and astronomer Guillermo Gonzalez. Gonzalez said this in their interview, quote, "The asteroids are mostly between the orbits of Mars and Jupiter. Our first line of defense is Mars, being at the edge of the asteroid belt. It takes a lot of the hits for us. Venus does too. If you want to get an idea of the stuff that would probably have hit the Earth, look at the surface of the Moon." End quote. Next parameter, our position inside the Milky Way galaxy. In order for life to exist, our solar system must reside just outside of the spiral arms of the Milky Way galaxy. This location is known as the Galactic Habitable Zone. Astronomers Guillermo Gonzalez and David Brownlee explain why this position in a spiral galaxy is so important for life. They talk about this in their movie, The Privileged Planet, which was put out by Illustra Media, and it's named after a book that astronomer Guillermo Gonzalez co-authored with philosopher J.W. Richards. Let's watch that clip.
Just as our location in the solar system is optimized for habitability, so is our location in the galaxy. We inhabit a spiral galaxy, which means it's highly flattened, it has a spherical bulge in the center, and it has spiral arms. And we live about halfway between the center of the galaxy and the edge.
Working closely with astrobiologists Peter Ward and Donald Brownlee, Gonzalez compared our position in the Milky Way to other regions within an often hostile galaxy.
The galaxy has a lot of dangers, and perhaps the most dangerous place in the galaxy is the galactic center.
Well, in the center of the galaxy, this density of stars is very high, and there are more supernovas and stuff. And there are things that could harass life right in the dead center regions of our galaxy.
You also have the giant black hole at the very center of the galaxy. And if it were to have a close encounter with a star passing near it, it would rip it to shreds and form an accretion disk around it and emit lots of radiation, particle radiation and electromagnetic radiation, gamma rays, X-rays.
While a black hole, exploding stars and deadly radiation would make complex life virtually impossible near the galactic core, the outer edge of the Milky Way poses other challenges to habitability.
In the outer regions, the situation is much more subtle. We live on a planet made out of iron, magnesium, and silicon, and oxygen. If we went in the more distant regions of our galaxy, out towards the outer edge, the abundances of these elements are lower.
There probably aren't enough heavy elements to build Earth-sized planets that can support life. So there's a happy median between the dangerous galactic center and the outer edge of the galaxy.
Gonzalez, Brownlee, and Ward labeled this region, where complex life is possible within the Milky Way, the galactic habitable zone. Their theory was first published in 2001 and has since received growing acceptance among astrobiologists.
There's a lot more research that needs to be done to determine just how wide the habitable zone is. But I think there's general agreement that yes, there are definitely places in the galaxy that you cannot have civilizations because they're very dangerous. And there are places where you just have a very low abundance of heavy elements.
While these obstacles to habitability are minimized far from the core and edge of the Milky Way, Gonzalez has also identified large areas within the galactic habitable zone itself, which are less hospitable to complex life.
But wait, there's more. The spiral nature of our galaxy. As it turns out, spiral galaxies are the only kind of galaxies that can have life. Astrophysicist Hugh Ross observed, quote, "In elliptical galaxies, star formation ceases before the interstellar medium becomes enriched enough with heavy elements. The problem with large, irregular galaxies is that they have active nuclei. These nuclei spew out life-destroying radiation and material. Meanwhile, most small, irregular galaxies have insufficient quantities of heavy elements essential for life," end quote. Additionally, Ross says that only 6% of the galaxies in our universe are spirals. This means that the vast majority of the universe is sterile. But wait, there's even more. We've looked at nearly 30 parameters that are needed in order to make a localized region of the universe habitable for life, but there are far more. In fact, there are way too many to cover in this video. Hugh Ross keeps an updated list of these parameters on the Reasons to Believe website, www.reasons.org. This compendium lists 402 different characteristics, the nearly 30 of the ones I talked about in this video included, that are needed to be just right for a galaxy, solar system, and planet to contain intelligent life. You can read about these 402 parameters by clicking the link in the description below. An argument for design. It seems to me that we can run a similar argument for design based on the local fine-tuning that we did for the universal fine-tuning. 1. The local fine-tuning is best explained by either physical necessity, chance, or design. 2. It is not best explained by physical necessity or chance. 3. Therefore, it is best explained by design. Once again, the first premise is indisputable. It's just simply a list of possible explanations. If the skeptic can think of another alternative, he's welcome to add it to the list, and then we'll consider it when we come to premise 2. But these seem to be the only possibilities. Let's move on to premise 2. Is it due to physical necessity or chance? Well, physical necessity is even more implausible for the local fine-tuning than it was for the cosmic fine-tuning. Surely the moon could have been more larger or less larger than it is. Surely that Theia could have traveled towards Earth at a faster rate or a slower rate than it did. Or it could have been bigger or smaller, or it could have hit the Earth at a bad angle. Any of these adjustments and more would render a local region incapable of supporting life. Yet all of these appear to be perfectly possible physically. Could it be due to chance? I don't think so. Even if one didn't do the math, one can pretty much see the implausibility of 402 different characteristics all being suited for advanced life, all just happening to come together in one place by mere happenstance. It is therefore neither due to physical necessity nor chance, which means it must have been due to intelligent design. Objection! Now we come to the point of the video where I look at atheistic objections to the argument that I have presented. Objection 1. We can explain how the solar system and Earth came about naturally. One objection to the local fine-tuning argument I've received is that we can explain how the solar system, Earth, the moon, and so on came about naturalistically. I mean, planets form when there's a bunch of matter, gas, and dust in the area, and gravity causes all of that matter to stick together until voila, you've got a planet. All of the pieces and stuff that make up a planet are gravitationally attracted to one another. And the same happens with stars. So we can explain in a perfectly natural way how celestial bodies form. The objection here provides me with a perfect opportunity to explain where the objector has misunderstood the argument. I am not arguing that a life-permitting region is so improbable that we must appeal to special creation or a miracle by God to explain it all. I am not at all saying that God needed to miraculously poof different galaxy stars and planets into being ex nihilo in order for us to be here. Rather, what I'm saying is that the odds of all of these just right characteristics coming together indicate that an intelligent designer made these factors fall into place. Now, they could, perhaps, have been poofed into being. God could have decided to do it that way. He could have just decided, poof, Milky Way, poof, solar system, poof, Earth. But we don't need to go that route. We don't need to commit ourselves to that view. In fact, I'm more inclined to think that the local fine-tuning is a result of God's ordinary providence. Now, what is ordinary providence? Ordinary providence is when God achieves his goals through naturalistic or natural means. Objection 2. The universe is a very big place. Given all of these potential life sites, life is bound to evolve somewhere. The most common objection to the argument that I've presented here is an appeal to the size of the universe. According to an article on Space.com, there could be as many as 100 billion galaxies in the universe. According to a different article on Space.com, written by the same author, there could be as many as 100 billion trillion stars in the universe. That's a pretty big number. Don't we have a very, very huge number of probabilistic resources? Doesn't that dramatically increase the odds that all of these characteristics could come together by chance? Well, Guillermo Gonzalez, who wrote The Privileged Planet, anticipated this objection, and he talks about it in the documentary named after his book, The Privileged Planet. Let's take a look at that clip.
In an attempt to estimate the probability of attaining this combination of factors simultaneously, some researchers have developed equations assigning a conservative 1 in 10 value to each factor deemed necessary for advanced life.
If every element has to be there at the same time, you have to multiply the probabilities. And that's what makes the probability at the end so small. You've got 10% of this and 10% of that, and these things rapidly multiply to exceedingly small numbers. The numbers on the order of 10 to the minus 15, which is 1/1000th of 1 trillionth. And it's a number like that that you have to compare to the 100 billion stars that are in the galaxy. 100 billion is a very large number, but 1,000th of a trillionth is much, much smaller. On their face value, these probabilities are speaking. What they're telling us is this can't happen, or this is very unlikely to happen in the galaxy. And that's where the evidence is pushing us.
There are many probabilistic resources in the galaxy, but on the other side of the coin are all these factors that you need. You have to get just right in order to have just one habitable planet like the Earth. And that leads me to conclude that yes, we're rare in the galaxy.
Objection 3. Why would God even make the universe so big if he only intended for one planet to have life on it? Some atheists object to this argument because if our world really was crafted by a masterful creator, surely he would have made it much smaller. Why would God create the universe with all of those useless stars and planets orbiting millions and even billions of light years away? While the planets in our solar system are conducive to life on Earth, how could these other stars and planets have any purpose? Richard Deem of GodandScience.org addresses this objection as follows, quote, "The universe could not have been much smaller than it is in order for nuclear fusion to have occurred during the first 3 minutes after the Big Bang. Without this brief period of nucleosynthesis, the early universe would have consisted entirely of hydrogen. Without helium, comprising 24% of the matter in the universe, heavy element production in stars is not possible, so that no rocky planets would have ever existed in the entire history of the universe. Likewise, the universe could not have been much more massive than it is, or life would not have been possible. If the universe were just 1 part in 10 to the 59th power more massive, the universe would have collapsed before life was possible. Since there are only 10 to the 80th power baryons in the universe, this means that an addition of just 10 to the 21st power baryons would have made life impossible. The universe is exactly the size it must be for life to exist at all." End quote. As you can see, there are physical reasons why the universe must be as large as it is. The mass density of the universe is part of the universal fine-tuning we talked about in a previous video. As I said in a previous video, and as I said earlier, in this video, there are 37 constants and quantities that must be just right for life. I only mentioned 9 of those because 1, only 9 were enough to make a powerful case for design, and 2, that video would have been extremely long if I mentioned all 37 of them. Now, some atheists might object that granted, the universe has to be this massive in order for life to exist, given the type of physical laws this universe runs by. But if God can do anything, as a result of his being omnipotent, then he ought to be able to craft a universe governed by different physical laws. Besides the scientific reasons that Richard Deem gave above, I think that there are spiritual reasons why God created the universe as large as it is. If this God, if this designer is the God of Judeo-Christianity, if he has revealed himself in the Bible, like I believe he has, then Scripture gives us two following reasons. In Isaiah chapter 40, verses 25 to 26, God says, "To whom will you compare me, or who is my equal, says the Holy One? Lift up your eyes and look to the heavens. Who created all these? He who brings out the starry host one by one and calls forth each of them by name. Because of his great power and mighty strength, not one of them is missing." God says that when we want to get a good idea of what he's like, then we should look to the heavens. Even though the universe is finite in size and depth, it looks infinite from our perspective. So, in other words, the sheer enormity of the universe can tell us that God's power is greater than that. God's love for us is even greater than that. His mercy and compassion are greater than that. It also tells us that since he knows each of the billion trillion stars in our universe by name, surely he knows the name of every human being on the planet. This can comfort us because it tells us that if God knows the names of the billion trillion stars in the universe, he knows each one of his children. He can attend to each one of us. When I look at the night sky, I'm overwhelmed by the enormity of the universe, but this doesn't make me think that I'm insignificant, that my existence has no worth, or that God doesn't exist or didn't create the universe, or that God doesn't care about me. No, instead it makes me drop to my knees in awe of God. If God created all of this, how powerful must he be to be able to manage and sustain all of it? God has to have enormous power to manage the entire cosmos. How mighty must he be to hold this massive universe in the palm of his hand? No, the size of the universe doesn't make me question my significance or God's love for me. It makes me fall to my knees in worship. If the universe were only the size of our solar system, the night sky would not likely have that emotional impact on me that God intended it for. That's why the message of Isaiah chapter 40 verses 25 to 26 is what it is. Moreover, in Psalm chapter 103 verse 11, we read, "For as high as the heavens are above the earth, so great is his love for those who revere him." If the universe were very small, God's purpose of using the universe as an analogy of his attributes and love for his children would fail. If the universe were small, it would tell us that God's love and power aren't very great. Now, in the ancient Near Eastern background of this passage, obviously the ancients did not believe the universe to be as big as we know it is now, but they still considered it to be pretty big. But this verse can have even more of an impact on modern Christians because we know that it's really, really big. So, for as high as the heavens are above the earth, so great is his love for those who revere him, can have trillions of times more impact for us than it did for the initial recipients of Psalm 103. My little red thing fell off. Okay. Objection 4. This is a God of the Gaps argument! Here we go. The God of the Gaps accusation rears its ugly head yet again. If I had a penny for every time that I heard this accusation when it came to an argument for God's existence, I could probably replace my Nintendo 3DS. I could probably buy my entire town Nintendo 3DSs. This is not a God of the Gaps argument. Remember what a God of the Gaps argument is. It is an argument from ignorance. It's on the basis of what you don't know. You see some scientific phenomenon, and you're like, gosh, I don't know how to account for that. Must be God. You see lightning, Norse people say, oh, there must be a God up there, wielding his hammer and making it all happen. But now we know that electrical currents and temperature and all sorts of stuff. I'm not a meteorologist, but we have scientific explanations for how lightning occurs now. Is the local fine-tuning argument that kind of argument? Do we just not know what we're talking? We don't know how to account for this within an atheistic worldview, so we say, whoop, Let's just insert God there. There we go. Now we have an explanation. No. Remember, we've got 3 options. Just like with the cosmic fine-tuning argument, we're making an inference to the design on the best explanation on the basis of what we do know. We're faced with 3 options: necessity, chance, design. Option 1 and option 2 are unreasonable explanations, but option 3 is not. If God created the universe, he could certainly have ensured that all of these life-requiring properties fell into place. To see the absurdity of this objection, see the absurdity of calling this a God of the Gaps accusation, consider this. Consider a man walking into his kitchen and he sees the cookie jar knocked over. His little daughter says, "It wasn't me!" But he responds, "Well, there's only 5 possible candidates for who could have eaten all the cookies in the cookie jar. It was either myself, your mom, your brother, your sister, or you. Now, I know from personal first-person perspective that it wasn't me. Your mom is allergic to chocolate, so if it were her, she'd be swollen, and she would be in desperate need of an EpiPen. Your brother is away at college, so it couldn't have been him, and your sister is only 2 months old. She couldn't have been able to reach it, so it must have been you." And the little girl responds, "You're using me of the Gaps reasoning. You're using me of the Gaps reasoning, Daddy. You can't say that I'm the one who ate the cookies in the cookie jar just because you can't think of another explanation. Do you even science, Daddy? Lol. Stop using me of the Gaps reasoning. We'll find an explanation for who ate the cookies in the cookie jar someday. Just ignore the cookie crumbs all over my face." This man would likely give his daughter a timeout for sloppy thinking. This inference is based on what he does know. He's not plugging his daughter into a gap in his knowledge. And anyone who says otherwise is being silly. Anyway, I hope you liked today's video. If you did, punch that like button like St. Nicholas punching Arius. And don't forget to go to cerebralfaith.net in order to find more apologetic content. I've got blog posts, I've got podcast episodes, I've got the YouTube videos arranged categorically on the website, and consider becoming a patron over on www.patreon.com/cerebralfaith. Your patronage means a lot to me. It really helps the ministry go far, and hopefully I'll be able to make even better quality videos if I can get some even more patrons. I may be able to get better video editing software. I'll be able to buy stock footage and stuff, and I'll be able to make even better quality content than I've been putting out even now. So, until next time, guys, keep using the brains that God gave you.